Hey everyone, so in this video we're going to be looking at the process of absolute dating. It's a follow on from our video on relative dating, and we'll go through the process of how we might absolute date fossils. So our learning intention for this video is to know a variety of absolute dating techniques, to understand some of the limitations of absolute dating, and to understand overall the benefits of using absolute dating as well as relative dating. So absolute dating encompasses a wide range of methods. So there's not just one way to absolute date. And we use these methods to determine the absolute age of an object or material. The ones we're going to mainly look at are absolute dating using carbon dating or potassium-argon dating. So here you can see, for example, relative dating we looked at was just comparing fossils in different layers and assuming which were oldest and the youngest, whereas absolute dating will actually give us a bit more of a time of how long ago those fossils might have existed. And you can see that there is some, I guess, accuracy with these plus or minus lines indicating that we're within about 5 million years for this dating method and about 10 million years for this dating method. So the first one we look at is the process of carbon dating. And this is a technique which we use to date organic materials by measuring how much carbon-14 is left in that material. Okay, now this works on the principle that carbon-14 becomes nitrogen-14, and that happens at a steady rate. So by using some mathematical formulas and by working our way backwards, if we measure how much carbon-14 is within an atom or within an organism, we can actually then date how long that organism has been decaying for. So it's really good for looking at things like bone or cloth or plant fibers, things that have that naturally occurring carbon within them. So the way it works is we use a half-life. Now, the half-life of carbon-14 is approximately 5,700 years. That means it takes 5,700 years for half of the carbon-14 to become nitrogen-14. And so by calculating how much is left, we can calculate how many half-lives there's been, and that then will help us determine how long that fossil is there for. Now, carbon-14 dating is good for around 60,000 years or less. If we go past that time frame, there's not enough carbon-14 really left to measure, and it starts to lead to inaccurate measurements. So here, for example, you can see we've got 100% of carbon-14, and when we get down to 50% left, it's taken around 5,100 years. Now, from half of 50, we get down to 25. That's taken another 5,700 years, and so on and so forth. So each time we half, we then add that 5,700 years. So it goes from 100 down to 50, down to 25, down to 12.5, and so on and so forth. It doesn't just go 100 to 50 to 0. It's about actually halving the number each time. And you can see in this diagram, we've got all red. Now we've got about half red. Now we've got about a quarter red. So that would be 1 half-life and 2 half-lives to get to there. So that's how we use half-lives for dating. And as I said, carbon's really good for up to around 60,000 years old. Potassium-argon dating is just another method using half-lives. And this is where potassium-40 will decay to argon-40. And again, it happens at a steady rate, and we can work out the mathematics behind that. Now, we usually use potassium-argon dating, not for dating the actual fossil itself, but for dating the rocks which surround a fossil. And that gives us an assumption that if it's next to a rock, the fossil must have been buried around the same time. Okay. Now, potassium dating is for much older fossils. And you can see here, it has a half-life of approximately 1.3 billion years. If you compare that to just under 6,000 years for carbon, it's a lot longer time for that half-life to occur. And again, we look at the half-lives and we work out what percentage of potassium-40 is left to work out our age. So here we'll use this diagram again. Okay, 100% means it's obviously just been buried. If we get to half or 50%, it's been 1 half-life, which is 1.3 billion years. If we get to a quarter or 25%, 2 half-lives, and so on and so forth. So as we keep checking number of half-lives, we can then work out how long ago was this organism fossilized or became a fossil. Some other examples of absolute dating is things like looking at tree rings. We can actually cut open trees and see how long they've existed for by counting the tree rings. So it's an absolute form of dating. We can also look at the magnetic fields in certain rocks. And lastly, there's a process that looks at the luminescence of rocks and seeing how long ago they've trapped energy for. These are other examples of absolute dating, but the one we need to cover mainly are those forms of carbon dating and potassium-argon dating. Again, if we've got absolute dating, we can then use index fossils of known ages and then be able to use that for relative dating or even more absolute dating as well. So scientists will not only use one process, they're going to combine a couple of different absolute dating techniques to get a more accurate picture. So in review, absolute dating encompasses a wide range of techniques, and often it involves radiometric analysis in the decay of atoms, so looking at half-lives. And they're limited when they can be used, but we often will use cross-referencing or multiple different techniques to ensure that they're accurate. So I hope this video helped you guys go through absolute dating.